Hello friends, today I'll be speaking on bisection or dichotomy method and a numerical analysis. My name once again is Isaac. I'm honored to you with you. I'll first of all speak on the background of bisection method, steps in solving bisection method. We'll look at the graphical example which kind of throw light on this bisection method. We then look at what algorithm to find approximate solution under bisection method, how to derive the number of iterations under bisection method, and then finally we'll look at some few applications of bisection method. So this method, bisection method, is also known as interval halving method. That was dividing an interval, continuous dividing of an interval until we happen to get a convergent value. It's a method based on division of halves, and it is one of the bracketing method in finding roots of a nonlinear equation, and is noted to be based on Bolzano's theorem for continuous function. So meaning that to begin with, the function must be continuous before we can apply this method. So this is what the Bolzano's theorem says. Is it if a function f of x is continuous on an interval a and b, and the functional value of a and b are less than 0, then a value c belonging to this interval a and b exists for which the functional value of c is equal to what? 0. So once if the functional value of c is equal to 0, it tells us that c is the root for the function. So looking at the graph that we have here, we have this interval a and b, and when you check the functional value here, it's negative. It's supposed to give, you have to be negative, and then when you check the functional value of b here, it has to be positive. So the product of the functional values a and b is negative. So once it's negative, it tells us that our root exists. Our root exists. So for us to be able to apply this bisection method, we consider these two intervals. That's, we consider this interval a and b, and we first of all find a midpoint, which our midpoint that we have here is what? Xm, and our xm is equal to what? A plus b divided by 2. So with this one, when you check the functional value for xm, it's going to give us positive. So once it happens to give us positive value, the functional value happens to give us positive, then we are confident that our root now will exist between what? Our a and xm. So once we are confident that our root exists between this a and xm, then we kind of forget b, which we can conclude that what we happen to get an approximation which is better off to use using xm and our a. So when you consider this interval again, we find the midpoint of it, assuming the midpoint exists around this very point, around here, then we kind of check the functional value. It is negative. It tells us that okay, there is a need for us to forget our initial a and then focus on the value here and our xm. We'll continue to bisect until we happen to get an approximate value. We might not get our exact value and the actual value, but we might get an approximate value which is closer to C. That is the convergent value. So this is how the bisection algorithm works. First of all, before we start the bisection method, we first of all check the functional value of A and then our B. When it's less than 0, as we have seen from the graph, then that one kind of gives us a confidence that our root exists. Else, when we happen to get a positive value, then it tells us that our root does not exist within that interval. So when it happens that we first of all check the first condition and then our root exists, then we can now go ahead to do the iteration process. So first of all, we find the midpoint, which is our C, and our C can be calculated as what? as we have seen, the midpoint a plus b divided by 2. So and then we will first of all do a check. If the functional value of c is equal to 0, then it means c is the root that we are interested in. So we kind of stop the iterative process. But when it happens that we don't get the functional value is not equal to 0, then we have to now go ahead to do a further check. So when you come here, we check the functional value of a and the functional value of c that we have obtained. When it's less than 0, then it tells us that, okay, our root exists between what, a and c. So if our root exists between a and c, then we don't need our b again. So we have to now, for computational purpose, we assign our c to b. So now the value of b is the same as the value of c. So we kind of forget of the original b that has been given to us. And when this condition fails, tells us that, okay, we don't need our a again. So meaning we have to assign our c value to a. So then when you come to the point 5, it says, oh, then we'll go to the beginning and repeat begin and repeat to convergence. So we'll go back again. Now once that we have done the new assignment, we kind of have what our a and b, a plus b, all divided by 2, and then continue the iterative process until we get what an approximate value. So now we want to, for computational purpose, we want to know from the word go, assuming when you are given a problem, we want to know the number of iterations that we have to perform for us to get a convergence. So we are not certain, and for computational purpose, when you are given the interval a and b, and then with a certain epsilon or tolerance, we kind of straight ahead find the number of iterations. And this is the formula for finding the number of iterations that we need to perform to get a convergent value or an approximate value. So now that we know the formula, we want to see how best can we be able to derive this formula. So we now first of all pose a condition that, okay, the approximate value minus the actual value should be less or equal to a certain tolerance. Okay. And then from the graph that we have here, looking at this interval, we have an interval A1 to B1. And then under bisection method, we did what a midpoint or halving. So first of all, find the midpoint of A1 and B1, which gives us our C1 here. And then we just go ahead. So when it happens that our root does not exist within this interval, then we cannot go ahead and then check for our C2, meaning we focus on this from this line to here, which is the same as what we have here. We bisect these two lines, the line into 2 again, which gives us our C2. And then when you come to this place, it happens that our root does not exist in this very interval. Then we have to forget of this line again, and then focus on what. Go ahead to find our C3. So we kind of bisect A3 and our B3 again, which we continue this process until we happen to get our nth bisection with a certain tolerance. So, but one thing that we have to know is we want to prove this. We want to use this graph or this understanding to help us to be able to derive the formula that we have seen above. So looking at the condition that we have already stated, we say the absolute value of our actual value minus the approximate value in the first bisection should be less or equal to what we have, the half of the interval here, which is the same as what we have here. And when we come to our second bisection, we kind of focus on what we have, B2 minus what A2, all divided by 2, as what we have here. So we have B2 minus A2, which is dividing the interval into 2. We kind of have what half of the interval, which happens to give us this one here. So we understand now our B2 is the midpoint of A1 plus what? B1, which to simplify this one, we factor our 2 out, which happens to give us what? 1 over 2 square. And when you simplify this one, we'll be having B plus what? A minus 2A, which eventually will give us our B minus A. So all that we want to do is we want to still maintain our original A and B that has been given to us. So we try to do a little manipulation to help us to be able to help us arrive at to help us use the actual A1 and B1 that has been given to us in the question. So when you come to the next bisection, which is the third bisection, we have our B3 minus what? A3 and a half of the interval. Give us this. And we understand our B3 is the midpoint of what? B2 plus what? A3, which to simplify, we factor the 2 out, half out, and it eventually give us this. Okay. When you do a little manipulation, we'll be getting what? B2 plus A2 minus 2A2, which will eventually give us equation 7. And then we can still understand that our B2 is what? The midpoint of A1 plus what? B2 all over 2. And then we still go ahead to factor our 2 out, our half out, and eventually give us 1 on 2 to the power 3, and which eventually give us what? We are still able to maintain our B1 and our A1 here. So, and when you continue this process, eventually get to the last iteration, we will happens to get, we're looking at the pattern, we will have a 1 over 2 to the power n into bracket B1 minus what? Our A1. So getting this one, then we can now go ahead to find the number of what? Iteration. So given a certain epsilon, when you are given a certain epsilon or tolerance, we want to know the number of iteration. So we happens to have our B1 minus A1 all on 2 to the power n should be greater or equal to what? The absolute value of Cn minus what? C. And then we now focus on these two terms. That's what? Epsilon greater or equal to the whole of this. And then we multiply both sides by 2 to the power n, which happens to give us what? This equation here. And then we multiply both sides by log. Multiplying both sides by log will happens to get this equation that we have here. And then we expand this very equation here, which gives us what? Log to the power 2 to log 2 to the power n plus log epsilon greater or equal to our right hand side, which is this. And then we kind of move the whole of this term to the right hand side, which happens to give us this equation here. Then we eventually divide this equation by log of 2, which eventually we happens to arrive at the actual formula that we have seen above. Okay, so now we will want to look at what? Application of this bisection method. So the first example that we want to look at is find a root of the function of this very function that we have here, x e to the power x equal to 1 on the intervals 0 and 1 using the bisection method. So we now rewrite the function, we consider our function f of x to be equal to x e to the power x minus 1, which is equal to 0. Then first of all, we will find the functional value. Given the interval, we first of all find the functional value of 0, which gives us -1. We check the functional value of 1 over x equal to 1, which gives us this positive value here. And then when you find the product of it, which is less than 1, this 1 times this 1 is less than 1. It's less than 1, 0. So 1 is less than 0. We are now confident that our root exists within these two intervals. Then we now go ahead to find our midpoint, which is what? 1 plus 0 all over 2, which gives a half. We check the functional value. With the functional value, we happen to get a negative value. So once we get a negative value, we kind of look at, okay, our 0 gives us a functional value of negative. So once we get a functional value for C1, which is equal to a negative value, then we kind of forget of this one, our 0, and then focus on what? This one, and then we kind of focus on 0.5 and then 1, which gives us what? A new interval. That's what? A2, B2, which is what? 0.5 and 1. So we now go ahead and then find our C2, which is 0.5 plus what? The midpoint, that's 0.5 plus 1 divided by 2, which gives us what? 0.75. We check the functional value. The functional value happens to give us a positive value. Okay, so once it happens to give us a positive value, and we understand that 1, the functional value of x is equal to 1 gives us a positive value. So now we get a better approximation. So we kind of forget of that one and now focus on what? Our 0.5 and 0.75. We then go ahead to find our C3. And with our C3, we happen to get what? 0.625. We check the functional value. The functional value is positive. So once it's positive, then we kind of understand that, okay, this value is better off than our 0.7. So we now forget of this 0.7 and then focus on this. We'll continue this process until we happen to get a convergent value. So this is a summary of all that we are trying to do. So we doing iteration from 1 to 10. And then we have what? Our A value here, B, C, and the functional value of C. So it's the functional value of C that helps us to determine as whether which one should we forget and which one should we maintain. So when you have initial values 0 and 1, we find a midpoint which is C, we check the functional value is negative. So 1 is negative, we understand that, okay, our 0 gives us negative, so we kind of substitute, bring our C value to replace our A here, initial A. So we focus on this value, our new A, and then our old B, which gives us a midpoint of 0.5, gives us a positive value. And then we understand that the functional value of B gives us what? A positive value. So we kind of forget this one and then substitute this one here. So we maintain our A1, and then our let me say yes, B1 here, B. Yes, we just bring this one here. Since we happen to see that the functional value of this one is positive, we kind of forget of this one and then bring this one here. So we then move ahead to find the functional value of this, of our new series 0.625, and it's positive. So one is positive, we cannot, this functional value here give us positive, this one functional value gives us a positive, so we kind of forget of this one and focus on this one rather again. So we check the midpoint, and this one happens to give us what? Positive. The functional value of the midpoint is 0.625. Check the functional value is negative. So once it's negative, then we kind of forget of this one and then replace this one here. It's pretty nice. So we now consider what? 0.5625 and then 0.625. We find the midpoint of it. It gives us 0.5938. Check the functional value and it gives us what? Positive. So once it gives us positive, so it's like the A side is negative and the B side is negative, is positive. So when this one gives us a positive functional value, then we have to, it tells us that we have to forget our old B. So our old B that we have here is this. So we just bring this one here. We continue on this iteration. That's how the computer program understands it. When you are checking the functional value of A and the functional value of B, when it's less than, then we mean the functional value of A and the functional value of C, then as we have seen in algorithm, then we know which one to substitute, we know which one to maintain. So in the 10th iteration, then we happen to get this functional value. Even this one still we are, this one tells us, even looking at the approximate value here, and then our 10th iteration, it's kind of tell us that, okay, the bisection method is really slow, really slow. So I think this one, after is a couple of iterations, we happen our value will be converging to this value, to 0.56714. So for when you continue to bisect, by in some exams you'll be limited on the number of iterations that you have to do, and this one kind of gives us the idea about how the bisection method really works. So we have a question of determining the number of iterations that we have to perform, and then one thing that you have to know is the number of iterations that you have to know does not depend on the function, but rather it depends on the interval given and then the tolerance that is given to you. So they say what one root of the equation. Okay, this equation can give us what several roots, but they are telling us that within this interval there is only one root that exists between this interval, and then it lies in the interval. Find the least number of iterations of the bisection method so that the tolerance should be less equal to 10 to the power negative 3. Then once we know the formula already, we plug it in. We have our B1, we have our B and our A. One is the log of what our tolerance, all divided by log 2, and it gives us what 9.9658, and approximately give us what 10. So for us to know the number of iterations that we need to perform, given this tolerance and the interval, we have to perform 10 iterations to get an approximate value for this equation. And the second problem that we also want to look at, what there's a one root of the equation, as we have seen, solved x e to the power x minus 1 equal to 0 lies in the interval 0 and 1. So find the least number of iterations for the bisection method so that our epsilon or tolerance will be less than 10 to the power negative 5. So we know the value of B and the value of A minus what the log of the tolerance, all divided by the log 2. It gives us 16.6096, and approximately we'll be getting what 7. Our n to be equal to what 17. So this has brought us to the end of bisection method, and I would like, if you like this video, please comment, subscribe, share, and like this video. Thank you.